Okay, so we're going to talk about the concept of electric potential, pick up where we left off from our discussion in the stairwell about how we can define an indirect measure of energy based on where you are in a field rather than where you are and how much charge or mass you have. So we're going to start off by looking at parallel plates and a test charge placed within the parallel plates. We choose parallel plates because we get a nice uniform field of intensity E, and it's just easier to start off with. So I'm going to draw our field lines just to remind ourselves that we have a uniform field throughout. Okay, so suppose we start with our test charge at the negative plate and it moves up, right, to the positive plate, okay? So remember, this is a positive test charge. In order to do that, it's not going to do that on its own spontaneously because it's attracted to the negative plates, if you will, at the ground. We must do work on the positive test charge. And the amount of work we did on it is nothing more than the force we exerted, and it's an electrical force. We have to overcome that force, multiply by the distance of separation, which is given as d. And we know from the E field intensity that the force is E times Q. And Q is the test charge that we chose, not the field charge that we have in the plates. Okay, now, because we've moved our QT up here, it has electrical potential energy. And when we release it, it will spontaneously go back down to the negative plate and give up that kinetic energy into, or that potential energy into kinetic energy, and we can calculate that as 1/2 mv squared. Or put another way, if we know the kinetic energy from the potential, then we can figure out how fast it's going. We'll do problems like that in a little bit. Okay? But let's say instead of 1 test charge, we brought 10 up to that spot. What would happen to the amount of work done or the amount of potential energy it has? Well, just like lifting a heavier object to the ceiling, the heavier it is, the more work we have to do. So we'd expect this to be 10 times the amount of work. And if we moved 100 to this spot, it would be even more difficult, and we would have 100 times the original amount of energy. The point being that the more work is done on a test charge, the more energy or it will gain or lose. So more charge means more work, means they have more energy. But is there something that all 3 test charges have the same about them because of where they are in the field? And that's the idea of electric potential. So it is very, very convenient to define a quantity that represents the amount of energy you have, or indirectly based on where you are, and that is done by doing energy per unit charge. Okay, so when you look at the energy done on something has divided by the amount of charge it has, you get a quantity that is based on where it is in a field, and we call that quantity electric potential. Okay, or more commonly it's called voltage, and that's given a symbol capital V, as we know from last year. Okay, so that's where that idea comes from. So the definition of voltage, EV, equals the work done on a charge divided by the amount of charge that you moved, energy per unit charge. We can often write that as U divided by QT, okay, depending on how the information you're given. But again, this quantity V is dependent on where you are, not the value of how much charge you have. So since V is independent of little q, we can rearrange this and come up with a dependent equation where we can say the work done to move a charge in a field equals the amount of charge I'm moving, that's a test charge, multiplied by the potential difference that I'm moving across. Okay, so technically what that should be is not a V, but a delta V, the potential difference. And we could just as well set that equal to the potential energy. So potential energy is Q delta V, or the work done is Q delta V. The units we talked about last year are joules per coulomb based on the definition, and that is called a volt, which is also given a symbol unit V, or uppercase V, and very importantly, it's a scalar quantity, meaning it has no direction. So when we go to look at multiple sources of a field and we want to know what the overall potential is, we simply add all the values. We don't have to worry about direction, which makes it extra convenient. So before we move on to doing some problems, I want to look at one other relationship that's important to know, and that's the relationship between the potential set up in a field and the electric field intensity, all right, between V and E. If we go up to back up to actually with these parallel plates here, we had an electric field E. Okay, that's uniform. And we also have, since there's different positions in here, there's different spots or different potentials. At the positive plate, it's at 1,000 volts, let's say, and the negative plate, it's at the ground. That's a convention, 0 volts. So as we move up into the field, like raising something above the ground, our potential goes up. And so we want to understand what is the relationship between that potential and the strength of the field. And it's a fairly simple derivation. So I'm going to start off with the idea of work. Okay, there's two ways to look at work. It's a force times a distance, and then in this particular case, it's also equal to Q times delta V, as we talked about in the definition of electric potential. Now, the force that we have to exert to get that charge up there is E times Q times D is the work equals Q delta V. And so we can see that the Q's cancel out, and we have a relationship that says the change in potential across surface is equal to the field intensity multiplied by the distance over which you move it, or where you are. So V and D are directly proportional. We can use that in the plates here. So if we start at 0 volts at the negative plate and 1,000 volts up here, and I put these little lines in here and they're equally spaced, then we can see this must be at 250 volts, 500 volts, 750 volts. And the point is, it doesn't matter what I bring at these various positions. So actually, let me choose a position. I could have 1 Q, I could have 1,000 Q. The potential is the same because of where it is, at 750 volts. If I want to know how much energy it has, U, then I just simply say, oh, it's Q times V. And we see that V changes with position, E does not. So let's try a few problems to help illustrate this more. Okay, so we're back to the parallel plates. Okay, this time we have an electron that is allowed to accelerate from the negative plate to the positive plate. So from an energy standpoint, we know that by the time it gets to the positive plate, it has kinetic energy. And if it has kinetic energy, it must have lost potential energy. So let's look at the change in potential energy. Okay, so the change in potential energy, whoops, I don't want to use PE. Sorry, let's use the U. So our U, our change in potential energy, is nothing more than the amount of charge that I'm moving, in this case an electron, multiplied by the change in electric potential. So our change in electric potential is final minus initial. So I put in negative 1.6 times 10 to the negative 19th coulombs for the charge of an electron, multiplied by, well, our final was 1,000 minus 0 gives us negative, right, 1.6 times 10 to the negative 16th joules. So that negative change in potential energy means we lost that amount of potential energy. And where did it go? It went into a positive gain in kinetic energy. Okay, so that's consistent with the idea that when we have a negative there, it would have a negative change in potential energy. Now, I'm not going to work this out, but if I have a positive here and I were to bring it, I'm sorry, I'm going to take that. Yeah, if I were to have it spontaneously go down, then in this direction, that would be a negative change of potential energy. So a negative change of potential energy or loss of potential energy is different in direction for a positive versus a negative charge. So you've got to be careful of that. And then we could ask, how fast is this moving? Well, we can just say that the kinetic energy it now has is 1/2 mv squared. We can plug in numbers, and I believe if we do it right, okay, we get about 1.9 times 10 to the 7th meters per second. So across a fairly modest change in potential, we're going 1/10 the speed of light. Now, suppose we had 5 electrons located at the negative plate. What would be our potential, not potential energy? So initially we had 1 electron, now we have 5 electrons. It's tempting to say that our potential is 0 here, but it's not so simple. This potential is based on a positive test charge. And since we have a negative test charge in here at the negative plate, we know that that 5e doesn't want to be near the negative plate. So in fact, its potential would be basically a negative 1,000 volts. Okay, because if we let it go to here, which would be at 0, okay, I take that back, it would be a positive, then our, let me work that out, I always get confused by this, our energy would be a loss in potential, so 0 minus 1,000, the negative times a negative, nope, this would be a negative 1,000 volts. I know it's very confusing, I'll clarify that in class. Okay, so when you have a negative test charge in here, these reverse and this becomes negative, so that everything works out. Okay, but the point is, it doesn't matter whether I have 1 electron here or 5 electrons there, I have the same potential. But the potential energy will be 5 times as great because the potential energy equals Q delta V, and since I have 5 times the Q, I'll have 5 times the energy. Okay. If the separation between the plates is 5 millimeters, what is the field intensity between the plates? Okay, that's pretty easy. Separation is D, field intensity is E. What do I know about the plates? I've got the V, so I can say that E would be equal to V divided by D. And so I have 1,000 volts. We don't really care about the magnitude, whether positive or negative in terms of change, divided by 0.005 meters. All right, and I believe if I do that right, I get 5 times 10 to the 6th newtons per coulomb. Well, actually, I'm not sure about that. That seems a little high. Okay, well, that was way off on that. I'm going to check the math. It's 2 times 10 to the 5th. Newtons per coulomb. Okay, that seems reasonable. It's less than our threshold for sparking, which is 3 times 10 to the 6th. We'll come back to this relationship, especially with capacitors, at another time. All right, so let's finish up with an important little distinction. Because the energy in part B is so small, we've developed a new unit of energy for situations like this called the electron volt. I don't know if we mentioned this last year. EV. And it's the end of the definition of an electron volt is the energy. So remember, even though it sounds like volt, energy needed to move 1 electron across 1 volt of potential. And so the conversion factor is pretty easy. It's basically what we're saying is 1 EV equals 1 electron times 1 volt. That's 1 electron volt. But an electron is how much charge in coulombs, 1.6 times 10 to the negative 19th. So 1 EV is 1.6 times 10 to the negative 19th joules. The point being, it's basically a Q times a V. So I can put in an electron in here for Q and get an EVs, or I can put coulombs in there and get it in joules. Okay, so try this problem. We'll talk about it in class, and then we'll pick up from there.